Yeah, thanks so very much indeed. A very warm welcome, everyone. I like to start talks by thanking the organizers for the kind invitation, but this time we are the organizers ourselves, so I don't quite know what to say. But that said, the team of IPAM has motivated us to submit our own talk, so here we are. So this talk, I will ask a question that's somewhat broad, but at the same time presumably relevant in this context when we ask whether we can reasonably hope quantum computers to have applications in machine learning and combinatorial optimization. The answer is no. Are there any questions? No, there's more to come. So one of the reasons we're here, presumably, is that not only do quantum computers offer promise advantages in computational tasks over classical computers, but this promise seems to be moving closer and closer to reality these days, creating a lot of interest in the field, mostly for good reasons, I'm tempted to say. The machines we have today are still relatively small and rather noisy, but then they seemed inconceivable not very long ago, creating an interesting state of affairs. The elephant in the room, however, in particular from the more mathematical perspective that we are interested in here, is the question whether we can reasonably hope noisy, realistic quantum devices to provide some sort of speed up over classical computers. Now, for very much paradigmatic problems, that seems to be the case. So the conceptually simplest experiments one can do in quantum mechanics is to do sampling experiments where one goes into the lab, not me, never let a theorist into the lab, but somebody else goes into somebody else's lab and takes raw data, and through the statistical interpretation of quantum mechanics, one would in this way perform a kind of sampling experiment. Now, there are some sampling experiments with so intricate distributions with funny tails so that one cannot resample that efficiently on a classical computer, or more precisely put, one cannot do a sampling classically efficiently up to a constant error in the total variation distance under reasonable mathematical assumptions. And this cannot only be done, but this has been done. In fact, I was at the time when this was the first experiment of that type was announced, I was in LA and in Santa Barbara visiting the Google crowd. It was hilarious that literally every Uber driver would be talking about this. It was the talk of the town. So that's interesting and, well, motivating. At the same time, it's also quite subtle. We just put out a review article with all the mathematical fine print of the complexity theory and the questions of verification in that, which is actually quite long and winding. Speaking of verification, it's a bit intricate and also ironic in that just going into the lab and taking data, one cannot verify the correctness of the experiment based on data alone. Or more precisely put, there's no algorithm that would take samples, and if the samples are perfect, would accept with probability, say, 2/3, and if you are more than epsilon away in the total variation distance, you would accept, say, with probably smaller than 1/3. That probably doesn't exist, which means that in a device-independent fashion, you cannot verify this, which is kind of somewhat intricate. So for this reason, people looked at notions of cross-entropy benchmarking that builds trust in the functioning of the device, that's sample efficient and computationally inefficient to see what's going on in the experiment. That said, if you have trust in the quantum devices performing experiments, then you can actually verify the correctness of these schemes. And that's kind of nice to see that you can take measurements, and based on those measurements alone, you can really verify that you're close in the total variation distance to the right distribution, but you cannot make predictions what comes out. You have to do the experiment, but you can take data and say, I'm right. But what is it? You don't know. You cannot efficiently say, but you can check the correctness based on quantum measurements. So this we've cooked up, and we joined forth with our friends in Innsbruck to see this in the lab. This also just came out some time ago. So verification can be subtle and also ironic in many readings. I advertise also Matthias' talk. Just after my talk, he will speak about the classical verification of quantum learning, showcasing again how intricate notions of learning and verification are related. So that's great. That's very motivating. So quantum devices can do something beyond classical capabilities. which is good. But then these sampling experiments don't really have any practical application. They're just there to sharpen our mind, what it means to do something interesting. That's encouraging, but of course we have to ask the question, like, what next? And the answer to this question depends very much on who you ask. If you ask more like physicsy-minded people, they will say, yeah, that's nice to have these sampling things, but the next step should be that we think about, say, programmable quantum simulators that are somewhat intermediate between analog quantum devices and digital full-scale quantum computers. And there have been interesting endeavors in that direction. Bayesian quantum algorithms are ubiquitous. They're everywhere. We've heard so much about them already, where the idea is to have like a quantum circuit in the center with some knobs, and then you would take data, and then there's a classical algorithm surrounding it, and you would then use that setting to find approximate solutions to combinatorial optimization problems or address questions in machine learning and so on. And there's instance of quantum-assisted machine learning, which is the reason why we are here today. And when thinking about this makes a lot of sense. We had the hype curve presented yesterday by Nathan. That was kind of cute. There's little denying that machine learning has changed the world we live in. Any algorithm that makes predictions based on past data is related to machine learning in one way or the other. There was this nice work by Juan on using machine learning for the study of materials and quantum chemistry and so on, who has actually used ChatGPT already. Okay, that's actually quite hilarious. So my student claims to have had the dialogue with ChatGPT saying, like, what is 4 plus 4? And the machine said 8. And the student said, no, my wife says it's 9. And ChatGPT said, oh, I'm sorry, you were right, it's 9. So, so that requires a certain level of sophistication. Anyway, so knowing that machine learning problems are clearly interesting, and knowing that quantum algorithms can speed up certain highly structured problems. So Maria made a big point out of that, which is interesting, that quantum computers are good in doing certain structured tasks, but there's still hope that quantum devices may offer advantages of some sort in machine learning problems. Or is there a scope for quantum-assisted machine learning in one way or the other? So ideally, we would like to have some sort of rigorous guarantee for state-of-the-art learning algorithms that are applied to real-world data sets. So data sets, say, from pictures of cats and dogs, stock market data, and so on. An algorithm like stochastic gradient descent and a model, say, neural networks in the classical realm or parameterized quantum circuits in the quantum realm. And we would like to see that in one way or the other, quantum devices can do better, fare better than the classical counterpart in a way. Now, this can mean many things. It can mean that you have a learner, and the learner takes fewer samples and comes earlier to a conclusion about the data set given, which would be an advantage in sample complexity. Or the learner could take fewer computational steps to come to the conclusion, which would be an advantage in computational complexity, or it could be an advantage in generalization bound as kind of a performance guarantee of learning algorithms. Even better would be like classical lower bounds and quantum upper bounds, if you want, where you think of a very specific quantum algorithm that's kind of designed and concrete and explicit on the one side, which is then found to be better in computational complexity than all classical learners, all models, all algorithms. So anything conceivable on the right-hand side, so that this specific well-defined quantum learning would be better than anything you can do in the classical realm. That would be the strongest possible quantum advantage in computational complexity you could hope for. That's presumably too much to hope for, but that is something we could dream about. We're still young enough to dream. Yeah.
Sometimes you read papers and they say we can claim that because if my computer is able to do Shor's algorithm, I can make a learning task that is factorize some number and just reformulate it into a learning task. And
we come to that in a second. Okay. We come to that in a second. Yeah, indeed. I mean, the thing is, that's actually the starting point we start out from. So we can ask, is there a quantum setting outperforming classical learners? And then, well, that's a very strong way of putting it, but then you can ask, can you achieve such an advantage? But for like highly fine-tuned data sets, so where, like following up on what you said, you give yourself the freedom to kind of back engineer the data set, yeah, but then have the advantage of this kind. So can we make progress in that direction? That's kind of the first technical part that we think of advantages in learning tasks. So what is the question at hand here? So you think of probabilistic modeling in the sense that there's a generator that takes randomness as an input and spits out samples from a given distribution that makes the concept class, and the task of the learner is to learn the distribution at hand. Now, learning can mean many things. It could mean that the algorithm takes these data and kind of tries to learn the classical description of the distribution as such, which would be density modeling. We've thought about this. I will not say so much about this here, but rather think of generator modeling where the learner takes samples and then thinks about them and then is able to spit out new samples from a kind of distribution that's close to the original distribution. That's kind of generator learning. So the task is to learn a generator of a given distribution, so of a concept class, a family of probability distributions. So can there be a quantum advantage? Following up on your question, so are there distributions that are efficiently quantum generator learnable, but that are not efficiently classical generator learnable by any classical learner in the sense that I just had anticipated, like anything on that side? No matter what. So let's be a bit more specific here. That was something that also Nathan had put up yesterday in a certain variant. That's the notion of PUC learning. But let's go over this for a minute. So this probably approximately correct learning of a distribution class is that you have a distribution class efficiently PUC learnable with respect to some distance if there's an algorithm that for every distribution within the concept class and every epsilon delta given access to an oracle. Wait, so oracles are dangerous, so you can sneak in a lot of computational power by having access to like very powerful oracles like Q-sample and so on. So here we are just looking at the classical sample oracles, so the one that would just take classical data you can write on a piece of paper, have on your laptop. That's the data access that you have, and you really read that into the quantum computer. So the reading in problem that Nathan has talked about yesterday is not here, it's just classical data, which is this oracle here. So outputs in time poly in all the parameters with probability at least 1 minus delta, so probably a generator of a distribution that is close in this distance up to epsilon, so it's approximately correct. So again, you take data and then the algorithm thinks and then it has the ability to spit out new samples from a distribution that's nearby in that distance with high probabilities. That's kind of the notion of PUC learning is a very, very mentally healthy way of thinking about such problems. Yeah.
Size of D, you mean the number of bits?
Yes, that's right. That's right.
The cardinality of the
exactly. So you poly in all these parameters. That's right. So can there be a quantum advantage? So are there distributions that are efficiently quantum generator learnable, say, with respect to the Kullback-Leibniz divergence or the relative entropy, if you want, and the natural sample oracle? Again, classical samples, classical data you can write on a piece of paper and so on, which are not efficiently classical generator learnable. And so is there such an advantage? And here the answer is yes, under very meaningful technical assumptions that exists, and they're not only an advantage exists, but in fact there's a super polynomial advantage of quantum learners over classical learners in this sense. So I will not go into the details of this proof, but I will give a kind of a high-level glimpse at what this is about. On the highest level, you have to show it's kind of quantum easy and classically hard in one way or the other. And if you've thought about these problems a bit, you might anticipate that the classical part is the hard bit and the quantum part is easier. It's often like that because you have to kind of find a kind of classical obstruction in a way. And here we are standing on the shoulders of giants, in fact, the shoulders of Kearns and our collaborators, the same Kearns that showed up in Patrick's talk yesterday in a compelling paper, where the notion of a pseudorandom function takes center stage. So that's a collection of keyed functions that cannot be distinguished from uniformly random functions. So there's, on the one hand, you have a couple of entry points on the domain. On the other one, you have a uniformly random domain by any polynomial time algorithm. And based on the concept of pseudo-random functions, you can kind of set up distribution classes that are defined by the Kern's generator, which means that you take the raw randomness x from your from a random number generator, and then you append the output of that pseudo-random function, and that can be shown to give rise to a concept class that cannot be efficiently classical generator learned no matter what. So the details are more intricate and more elaborate. So the argument is actually quite elaborate, and it's a relatively complicated polynomial hierarchy. But in the machine room of the algorithm is a kind of a one-way function, and that kind of is used to kind of set up a kind of Michali-Goldreich-Goldwasser tree construction to kind of formulate the pseudo-random function in this fashion. But one-way functions we know how to kind of revert in quantum information. Shor's algorithm can do that. And so with Shor's algorithm, we crack the hard-to-learn distribution class with a quantum computer. So quantumly, we can walk the tree backwards and crack the distribution, while classically, we can not do this. So these are kind of fine-tuned data sets and fine-tuned distributions. But for that distribution, you can show there's a proven quantum generator learning advantage. So quantum computers can learn more efficiently. In fact, not only more efficiently, but super polynomially more efficiently than a classical computer. And it's true in the sense that there's a specific quantum algorithm that's better than any conceivable classical learner, no matter what. That's nice, because the field exists. There is a quantum advantage in this strongest possible case. But again, it's like it's for a fault-tolerant computer. And it's like for highly structured, you anticipate, it's like highly back-engineered data sets, even though the devil is in the detail to make this work. It's not just applying Shor, but you have to work on this. There's also a companion paper that was done by the IBM group that looked at kernels that showed that there is in principle an advantage of a kind, which is nice. It's very encouraging. Quantum computers can do better, but there's more to say about this. Yes?
Sorry, can you repeat again what the data is? What's one data point you would use for the
okay. These are back-engineered data, so it's very hard to say. I mean, they use these pseudo-random functions and so on, but that's a classical data, but they're it's hard to spell out. I mean, it's not very concrete. I mean, but it's explicit. I mean, we can spell out what the data set is, but I mean, it has no interpretation other than.
But one data point is a function, right?
It's a bit string.
Well, the bit string is the bit string is a lot of numbers, the instances. That's right. Was another question? Yeah.
Yeah, just to be clear, this is contingent on an assumption of classical some classical.
Of course, I mean it makes basically use of the hardness of the inversion of the RSA encryption function. That's right. I mean there must be some assumption. I said it in fine print. Of course, that Shor's algorithm is solving a problem that's classically hard is assumed here, and that's basically the only technical assumption that enters. But of course, you have to have such an assumption. That's right. I had it in the lower right corner here. Very good. So that's nice. The field exists. There is an advantage, but then again, it's using fault-tolerant computers, and it's using you said it. I mean, it's highly structured data, not pictures of cats and dogs. So when we were thinking a bit about what next, actually, we had this discussion with Maria yesterday in the lunch break. So I'm putting that in now. What could be a next step? And it's not so easy to make next steps. We have something to say, and there's also more work coming. But in this endeavor, we thought, okay, can we maybe give up something, but then have a closer contact to less structured data and more real-world data, actually pictures of cats and dogs if we want, and do something in that realm. That was our next step, following up your line of thought. And we were thinking, good, can you think of classical networks, large-scale classical networks, and look at the task of training classical networks and possibly training classical networks with a quantum computer. And that was actually quite interesting, where we looked at large-scale networks that we pruned by chopping off the small weights in the network, and looked how one can do the training of these networks with stochastic gradient descent compared to quantum algorithms that were making use of or devising a variant of HHL for training sparse, pruned classical networks in a kind. So this we set up, and we also found performance guarantees. And we have like performance guarantees of these sparse learning models with a quantum algorithm that has no problem of uploading. So for the sparse of these circuits, you can also efficiently upload the setting, and you can again find a super polynomial improvement of the quantum training over a classical training based on stochastic gradient descent. I mean, there's good reasons to believe that this kind of Yuan-Tang L2-norm sampling type is dequantization is not dequantizing this. Ultimately, it's difficult to be prone against any sort of dequantization, but it's kind of nice to see that for that type of setting, there's a super polynomial separation over meaningful classical algorithms on the quantum side. It's kind of a new avenue to think about this. It's kind of interesting, in particular since the outcomes were actually quite impressive and the performance was quite nice. We also couldn't resist on using this on the C400 data set, like a standard data set for machine learning that includes lots of images, and it performed quite well on that. That's also included in the paper, which was one of the reasons why it took so long to do it. Actually, one of the authors is even here, in principle, but I think he's not in the audience at the moment. Okay, anyway. He's in principle here. So we also have pictures of cats and dogs, so we use that. That's actually my own cat. It's new. It's kind of cute because I have this habit of getting up very early and having my coffee in the morning. The cat is new, and the cat seems to think that's what we do in our household. So the cat also gets up early, sits on my computer, and is like using his claws to have some coffee. It's kind of cute how the cat mimics my behavior. Anyway, so quantum algorithms have a super polynomial speedup over stochastic gradient descent in training fluid classical networks. It is what it is. I mean, it's a separation, and it's a kind of new approach of thinking outside the box, of trying to see what we can do with quantum devices for less structured data in a way coming from a different direction. That's my long answer to your question, Maria, yesterday. But again, it's for unstructured data. Yes, good. That answers also your point. But it's still using fault-tolerant quantum computers in a way. Good. So that's nice. So the field exists. Quantum devices can do better in principle than classical learners. That's true in this kind of highly reverse engineered setting that has shown in the machine room of the argument, but also in this kind of idea of training classical networks with quantum devices, which is nice. The field exists, but we have to move on. So we have to ask, like, can we find a more near-term quantum classical separation? So is there probabilistic modeling tasks where a quantum computer can perform well on real-life data sets, maybe presumably more in the NISQ arena? And that's not so easy to make progress on, because after all, like what we said before, was on highly structured data, and pictures of cats and dogs are not so easy to parameterize and capture mathematically precisely. Also, they're dealt with GANs or restricted Boltzmann machines, and that's more difficult to analyze. So in a way, we need a kind of a vehicle to make progress here. And what we thought about here was to think of quantum circuits followed by measurements, which are like the inner part of hybrid algorithms that have knobs and have, like, you do measurements, you take data, and there's a bigger classical algorithm around that. Because for that, you run the circuit and have two measurements. They are also featuring in these quantum advantage / supremacy settings where you take data and you have distributions that are hard to sample from, they're hard to simulate, and you can ask, are they hard to learn as well? So you can look at these different connections. So these machines are also called quantum circuit Born machines, for the Born rule coming in when you apply, like when you compute the probabilities at the end. So the specific question we asked was, can a learner learn the output distribution of quantum circuits? And this we looked at from several angles, and that was a kind of a crime story of the first league with ups and downs and positive and negative results, which was kind of cute and interesting to see, and I name a couple of them in the following. So the first one is, well, we already know that they're hard to simulate classically. Well, we have these quantum supremacy arguments, for sure. If you have very deep quantum circuits. D is the depth of the circuit. You can approximate arbitrary distributions arbitrarily well. Presumably that's hard to learn. For d equals 1, you have a product distribution. That's presumably easy to learn. So at what depth, say, does the hardness of the learning kind of set in?
Sorry, what are the inputs exactly? You're putting in a uniform distribution?
So one model would be like have a local circuit, like nearest neighbor local, and then, I mean, we discussed this yesterday, like maybe have random 2x2 gates, and that would give rise to the family of circuits. But yeah, locality matters. So for now, we will look at local circuits in that sense that you have like a geometric local setting. So where does hardness set in? Like short circuits, you can learn longer, we can presumably not learn. So what is going on here? And the first insight was that under a meaningful technical assumption that if standard secure pseudorandom functions exist, then at a depth that's of the almost order of a linear depth, it's already hard to compute, to learn the output distribution, both in the generative and the density modeling sense. So if you're already a bit more than linear in depth, you cannot learn the output distribution of a quantum computer. In fact, both for quantum and classical algorithms. So that's kind of interesting to see that not even the quantum computer can efficiently learn the output distribution of a quantum computer. So this time the pseudorandom functions cannot be broken by a quantum algorithm, so there's no quantum advantage in a sense. Yes?
I know this question is stupid, I should probably read the paper better, but does learning here mean also expressivity? Because it seems like if I cannot computationally prepare distribution and sample from it,
yes.
Isn't that the so if
I mean, it's meant, to be precise, it's meant in the Park learning sense. So in the sense that I said earlier.
But if a model cannot express the ground truth, then do I even have to worry about if it can learn it? So learning means the way to get there, find it, discover it. I'm just like trying to understand if
maybe I can answer quickly. Like you have a very, very good point. There's two very different computational problems here. The one is you're given a description of the circuit and you should sample from its output distribution. This is like quantum advantage experiments. And we know that that's hard. But here you're given samples from the distribution and the task is to sample again. And so it's a different computational problem. But in both of these problems can be hard, but there can still exist classical circuits to sample from the distribution. So actually it's unknown whether or not there exist classical circuits to sample from these distributions.
You might not be able to construct it, but you might be able to learn it somehow.
That's right. I can't remember. Also, 3 slides from now, we'll come to that. I mean, thanks, Ryan, for the explanation. I will also say a bit more about this, and maybe like 3 slides from now, you can ask your question again. But it's okay. Like already at linear depth, basically, you have distributions that you cannot Park learn, both in the generative setting, so you spit out new samples, and the density modeling setting, you want to learn the distribution, both quantumly and classically, which is kind of funny that, I mean, already at linear depth, this is kind of the case. And also, it means that there's no quantum advantage, but it's kind of bad news if you want, because it's kind of a hard learning task also for a quantum computer, and that's both true for the classical and the quantum setting. If you think of statistical query oracle, so that's kind of a computation problem where you have access to an oracle that, when queried with functions phi, would promise to give an output, like a number as an output that's guaranteed to be like tau away from the expectation value, then not at linear depth, but at logarithmic depth, learning is already hard, and that's very natural as a model because usually we take expectation values anyway from distributions, and here already at logarithmic depth you find that learning is hard. And that surprised us quite a lot in that logarithmic, I mean, these are geometrically local circuits, and already at logarithmic depth under this statistical query model, learning is hard. But that's kind of weird in that, I mean, these logarithmically deep circuits, they're clearly efficiently classical assimilatable, both in the weak and the strong settings. So these are settings that are easy. I mean, that a bit follows up on your question, that they're easy to simulate classically, both in the strong and the weak setting, but they cannot be learned in the Park sense under the statistical query setting. So motivated by this, said, wait a minute. So what's the, yeah?
They're easy to sample from?
You can, yes.
Computing expectations, I agree, but the sampling?
Wait. Sorry. I mean, no. Wait. That's right. So that's right. Good point. No. So that was okay. I come to something. No. Right. But very good. You can compute. I mean, they're geometrically local, right? You can construct tensor networks, so you can put expectation values. That's right. But presumably you cannot sample from that because you have like anti-concentration in log depth, and then that's right. Good point. But it's still fine what I said because I was talking about expectation values, but cut the sampling. That's right. Yeah. Good. But I come to sampling in a sec, and then I say this. So motivated by this, we asked, like, what is the connection between simulation on the one hand and learning problems on the other hand? And in the literature, you see lots of statements of this kind that if you have to simulate, then you have to be able to learn. If you can learn, you can also simulate. There's lots of kind of suggestions on the connection between simulation on the one hand and learning on the other hand. And we were looking at the question how they are precisely related. And in this context, it seems very natural to think about Clifford circuits. And so Clifford circuits, we know, are easy to simulate. Now I'm right in that you can strongly and weakly simulate them. You can compute expectation values. Well, that was one of the first results of the field. But you can also sample from the output distribution. So no typo now in a Clifford circuit. But then if you have the output distribution of a Clifford circuit, you can also learn the output distribution efficiently. So that's nice. That works. It's kind of easy. And that's true for Clifford circuits of any depth, because there's a Clifford group and so on. The depth doesn't really matter. And that's much less trivial than you might think. I mean, it's not super deep, but it's less trivial than you think because there's also many Clifford circuits after all. But the Clifford circuit output distributions are uniform over a finite subspace, over the finite like a vector field or vector space over a finite field, and then you can make a kind of Gaussian elimination type algorithm to learn the distribution, even though there's many Clifford circuits at the time. So that's nice. So Clifford circuits can be simulated weakly and strongly. You can sample, you can do expectations, but you can also learn them. That's nice. So learning, simulation, that's all easy in the Clifford realm. Now we also know that if you add T-gates to the Clifford circuits, you can make them universal. Right? That's kind of the plain vanilla setting to think about fault-tolerant quantum computers. People think of like transversal Clifford gates in a way, and then there's the bit difficult T-gates that you put in to beef up your non-universal algorithm to a universal algorithm of a type. So clearly, if you add as many T-gates if you want, then you can generate arbitrary circuits, and you can approximate arbitrary unitaries arbitrarily well. But say you have a Clifford circuit, and you start adding T-gates, at what point does it become hard to simulate, to learn the output distribution? That was kind of our question. And so we kind of had the Clifford circuit, we kind of put one T-gate out, and had it, and placed the T-gate. And clearly with one T-gate, I mean, you can clearly still weakly and strongly simulate the setting, because what is a T-gate? It's a gate, so you just look at all branches, actually both branches, and you simulate that. Yeah, that would in fact work for a logarithmic number of T-gates. But you take this one T-gate, and it turns out that one T-gate makes learning hard. That's kind of funny, because clearly, again, with one T-gate, you can easily simulate, in the strong and the weak sense, the output distribution, but the learning task is rendered hard by having a single T-gate. And that's shown by a reduction from the parity learning with noise problem, but there's no noise here. It's kind of an effective noise by the T-gate in the setting, which is kind of funny because, again, simulation is perfectly easy. So circuits with logarithmically many T-gates can be efficiently simulated, but you cannot learn the output distribution. Single T-gate renders learning hard, which is counterintuitive if you want. So that's interesting. There's a question. I think the speaker should unmute and.
Yeah, I have a question. Maybe to clarify, simulation is only about the computation. The learning involves the statistic inference. Would that make the difference between the simulation and the learning?
Yeah, that's a fair point. I mean, yeah, the point, one is about statistical inference and the other one is about the simulation. That's right. I mean, it's not the same task, but that's also why it's different. I mean, one is easy there, or the other one isn't. That's right. That's a good way of putting it. It's still surprising that a setting that seems so simple on the simulation side is hard to learn, but that is a valid point. So that's all I say about this. I advertise Ryan's talk just afterwards, after Matthias Kara's talk. He will follow up here, and we'll say a lot more. Like there's 2 topics. The first topic will be to think about parametric quantum circuits, also to look at average case hardness in this setting, following up on this. So single T-gate randomized learning hard. There's one, I'm still very nice with time. I'm almost through with the talk, and there's lots of time for questions at the end. But let me maybe procrastinate a little bit. I take the liberty to procrastinate on this because it's a bit off topic, but on the topic of T-gates and Clifford circuits, I find this an interesting observation. One day I will give a talk on the cup of tea or something. So who knows what a unitary design is? Most? Yeah, okay, most. So a unitary design is a finite collection of unitaries with the property that it mimics the low moments of the Haar measure. So we would have a unitary K design if the first K moments are the same as for the Haar measure. And you can have approximate definitions like that based on the diamond norm. That's very natural of having approximate unitary designs. So they're ubiquitous in quantum information. You have them in benchmarking, in like foundational issues on thermalization, whatnot. I mean, they're basically everywhere. I mean, like in this kind of out of time model correlation functions, people get very excited about unitary designs. Now, we know that random Cliffords are unitary 2 designs. That's why they feature a lot in randomized benchmarking. But they just fail to be, they just fail to be 4 designs. They're 3 designs. And that's a little bit, there's a bit missing from a representation theory perspective to be 4 designs. They're just 3 designs. So how can you make an arbitrary order design from a Clifford circuit? You have a Clifford circuit, and then how do you make 27 designs out of them? Well, that's easy. Take like 1,000 qubits or 10,000 qubits, a big system. And then you say, if you have a Clifford circuit, it's a 3 design, failing to be a 4 design, gracefully, as they say. And then you start taking T-gates and placing them. So how many T-gates do you need to uplift a 3 design to an arbitrary order? So like a 27 order design for 10,000 qubits. This was something that we worked very hard on. That was a chainsaw massacre in representation theory and 3 years of work. But the answer was kind of compelling in that the number of T-gates you need in the ordinary sense of diamond norm approximation is independent, is a constant, independent of the system size. So if you have like 10 million qubits, I wish, but never mind, and you want a 27 order design, then you place like around 5 or so T-gates, and that uplifts this to a 27 order design. So the universality kind of is at the seat of these T-gates and kind of amplifies itself to the entire system independent of the system size.
So the 27 matters, but
the 27 matters. Indeed, there's a polynomial dependence on 27, very nice point. But the n doesn't matter, but the order matters. Of course, the higher the order, you need more T-gates, but the size doesn't matter. Very good point.
there's an epsilon dependence?
There's also an epsilon dependence, but that's a good point. Even the sense of approximation matters. Yeah, that's a good point. But in the diamond norm sense, the epsilon matters. It's part of the equation. But n doesn't matter. Yeah.
And the size of the Clifford circuit that you started with is dependent on the system size, right? Or not?
No. Well, only in the well, the worst case depth, that's right. I mean, there's a mild dependence of the Clifford circuit to the system size. If you want to have an arbitrary circuit, that's right. But that's a mild dependence, that's right. But the number of T-gates is dependent on epsilon, that's right. It will heavily depend on the order. It's pretty unforgiving in the order, actually. But not on n. That's kind of funny. Anyway, I thought that was kind of interesting, in that the universality can be a seed thing that amplifies itself to arbitrary orders. So when we put out this paper, so we were like really proud of this, and then we were a bit carried away. So in the end, because we thought for such a technical result, you can be a bit funny. And then we called this paper quantum homeopathy works. Because that was it. You have the medicine of the T-gate, and you can amplify this over and over again. It never stops working. That's quantum homeopathy. And we submitted this. We didn't dare to, we submitted it to CMP, and it was also published there, but that's a German journal. You don't make these jokes. But on the archive, we had it like that. But it was hilarious about emails we got afterwards. Like, oh, you've shown that quantum homeopathy works. So, it was really, really fun. Anyway, here's the thing. So you can uplift T-gates to an approximate arbitrary designs with a constant number of T-gates. Again, with an epsilon dependence, yes. With a dependence on the order of the design, but not on n. So pathetic. That's the technical result. It came out earlier this year. Very good. Very good. So we look at the connection between simulation and learning. That's intricate. There's obstruction to proving quantum advantages because sometimes the quantum computer cannot learn its own distribution. So this is also a bit negative news on finding near-term advantages. There's more to say about this. We have a paper in the making that's a bit more positive again, but overall there's ups and downs in the field. But for us, it was like first rigorous insights into the learnability of outputs of quantum circuits, and Ryan will say a lot more about this like an hour from now in a way. So what we did here was actually much motivated by a nice paper from Edinburgh that looked at the question. I mean, to be fair, I mean, I like the paper. It didn't have many results, but it's not meant as a criticism, but it was kind of suggesting the mindset and the question. And since they were looking at Born machines and the question of quantum advantages in Born machines, they actually called the paper the Born supremacy. and then since our paper then in the end kind of looked at the problem carefully in a more mathematically mindset and looked at the identity of the problem, of how the advantages are precisely set up in a rigorous fashion. We first wanted to call the paper the Born identity, but then my co-authors voted against this, so we have a very technical title in the end, but never mind. Good. So 41 minutes into the talk. I have 60 in total, but I leave time for questions, so maybe I already come to an end soon. So maybe let me say that this, what I just said, is like kind of past pro total, like a bit of a selection of a bigger program in my team, where we looked at what like near-term quantum algorithms, quantum computers can possibly do in meaningful learning tasks. We heard a nice talk by Yuri yesterday on strong limitations for quantum error correction in log depth. There's the mathematician's joke that log is upper bounded by 4. It's not such a bad joke if you think about this. You have to go to very deep circuits to hit 4 with log. That she explained very nicely. So there's obstructions to quantum error mitigation. Noise is bad. But then we also found that noise can be a good thing. If you think of variation algorithms, there's this kind of narrative that if you wobble a little bit, then you can get out of saddle points when you are stuck and so on. And this we could put on a rigorous footing. That's indeed right. And we kind of built on results in classical machine learning to show that sometimes in precise settings you can say what noise you can add, and then you provably converge to the next local optimum nearby. So noise can be also helpful in certain variational settings. We thought how symmetry can help in variation algorithms. Sometimes it can help, sometimes it can help too much, and that you can dequantize settings, but most of the time symmetry is helpful in variation algorithms. We have worked a lot on Hamiltonian learning. Don't get me going, otherwise I give another hour talk. I constrain myself, but I'm very happy to talk more we had a nice poster yesterday on Hamiltonian learning, and we did work, for example, also for the Google team calibrating their quantum chip. We thought about gadgets, like Hamiltonian gadgets, to tackle barren plateaus that we heard about also yesterday quite a bit. Will you speak about expressivity of quantum kernels? So, okay, that's something we could do. Generalization bounds is something we thought quite a bit about. There will be a talk by you later this week on generalization. There's a technical result first, but there's also a very kind of provocative paper in a way. That's a bit of a badass paper that you will speak about later this week that I advertise here. And maybe the most compelling insight is here that I wanted to quickly say is that, I mean, we also looked at classical surrogates that along the lines also Maria has mentioned, that on building on her work also on the kind of full picture of certain classes of data real loading models, where we were thinking about in what sense and when you can actually dequantize classical such models and have a classical surrogate for that setting in evaluation and in training in particular, and when you can't do that. And I think there will be Ryan's second theme that I hear loudly advertised that we will speak about an hour from now, and we'll say a lot more about this using random Fourier features. Good, but the last point I wanted to make before I conclude is, and I had advertised this in the talk title, so I better say something about this, in the coda whether we can hope to see advantages for combinatorial optimization in a way. And that's something that is receiving a lot of attention these days. I mean, there's no day when not somebody looks at some Quawa optimization problem run on some data set, and that's nice. We need this type of heuristics. That's good and important. I'm not dismissive about this. But then we should also be clear about what we can hope for. So in Germany, there was a That's the Handelsblatt, that's the leading economical monthly newspaper we have, and there was a title thing said, quantum computers can solve every problem in the world in polynomial time. I said, whoa, I mean, the marriage problems of my neighbor, it cannot solve. And that's only the tip of the iceberg. There's lots of problems it can't solve, right? Sorry?
You're skeptic.
No, in particular, I mean, like, the common optimization problem we think about in combinatorial optimization, like integer programming, so they're NP-hard in worst case complexity, which means that there is no polynomial time algorithm in worst case that offers a solution of this optimization problem. But that also means, as we all know, that there will not be a quantum algorithm that will offer a polynomial time solution for all instances. But what's even on the plate? So what we asked was, is there a quantum advantage of a kind? And second, in what sense can this be true? Because it cannot not mean that we solve NP-hard problems in polynomial time on a quantum computer. Yeah? So in what sense can this be true? And this I keep short. I rather advertise this. But the point is there is advantage. There's super polynomial advantages. And a quantum computer can approximate hard instances originally from the hardness of inverting the RSA encryption function. That picks up a question that you had. Again, the hardness of inverting the RSA function is coming in polynomial time. So in a way, the easy hardness line is shifted. And there's some problems that you can approximate efficiently well on a quantum computer, while you cannot approximate them well efficiently on a classical computer. And that is true. And that's true for practically relevant problems such as integer programming. And again, Shaw's algorithm is in the machine room. I say this very clearly. But the reduction is actually still quite intricate. So it goes via like Occam's razor problem, then a formula carrying problem, and then integer program as a polynomial reduction. But a quantum computer can approximate hard instead of integer programming, a practical optimization problem well, while a classical computer cannot do this, again, under the assumption of the hardness of the RSA encryption function, but no other assumption, which is kind of nice to see. So there is a super polynomial speedup. That's, again, good to know. It's a CARP reduction, so it's actually explicit also. I mean, there's a student now working on the explicit instances of integer programming. That's good news. So we have clarified, so provided guidance what to hope for. It's explicit. It's not variational. I should say this. I couldn't resist on spelling out a Hamiltonian problem, so we have given a Hamiltonian so that the solution, like the quantum algorithm, would provide an energy of that Hamiltonian to a promised accuracy, but it's still not variational. But we put it into the context of a variational algorithm. It's also constructive. We find classically hard instances, so we can spell them out, but the connection to quantum approximate optimization, we do not know. I mean, that's just a baby step. I mean, we said this. There's this big desert in the middle of nothingness, and we come from every side and try to make progress. So that's at least clarifying the sense in which we can hope for a quantum advantage for optimization. And it's a practical problem like integer programming that makes sense. And for that, we can show in what precise sense we can hope for an advantage. And it's explicit, so we can even spell out the instance of a kind, which we were quite happy. That was our kind of Christmas present before Christmas last year. Very good. Outlook, 48 minutes. Good. Just in time. So in this talk, we asked whether we can reasonably hope realistic quantum devices to provide a speed up over classical computers. That's the question of the talk, and of course, that's also a bit the question of the field, if you want. That's not so easy. And we found some good news. Like, yes, there's a super polynomial quantum advantage in PAC learning in a very precise and very stringent sense, but for completely reverse engineered distributions. And not practical, no pictures of cats and dogs, but at least one can kind of say something in principle that this quantum advantage for highly structured problems is there in principle. But how much structure do we need? It's not so clear. We also found that a single T-gate renders learning hard. So in the second technical part, we found some obstructions against having advantages for short quantum circuits of a kind. We found that a little noise can be a good thing. So if you're doing variation algorithms, sometimes like stochastic noise can help and make sure that you're not getting stuck. So it can be nice to have a bit of noise. But then we also found that error mitigation already fails at log-log deep circuits. That's exponentially improving on known obstructions against error mitigation. So error mitigation is just not scalable. It's good for what it is, and there were ups and downs also with IBM recently, and I'm highly respectful of their work. It's beautiful work. But one has to be aware of the fact that it's just not scalable. And I mean, you make this point nicely yesterday. I mean, there were already early hints to that effect, but this is a very strong way of putting it, that even a log-log, there's no way you can undo this. We've also found a super polynomial advantage in optimization, at least in principle. The title even said it's an in principle advantage, but it's for a practical problem. It's like integer programming. That's what the Deutsche Bahn would presumably use. It's explicit, but again, it's not variational. We don't have this, but one has to start somewhere, so that's kind of a baby step, I think, in a healthy direction. But can we do this more practical? Can we relate this to variational quantum algorithms? Let's see. I think that's a good homework task to be given for the next step. So can we hope noisy, realistic quantum devices to provide a speed up over classical computers? So here's my answer. Definitely maybe. So on that note, I thank you very much for your attention, and I'm looking forward to questions you might possibly have.